Okay, thank you. First of all, I want to thank the organizer. Thank you, Tatiana, for the introduction. And also for organizing this very nice workshop in this place. So, of course, I put a postcard of the place where I live because it's very nice, but let's go on. First of all, I want to acknowledge my collaborators, Mario Cuoco from CNR in Salerno, and Carmine Ortiz and Claudio Garcello from my same university in Salerno, and also collaboration with people in Pisa, Luca Chirolli, and Francesco Zotto, who is an experimentalist, and also with all these experimental groups. Also, I want to acknowledge, there is some noise, I want to acknowledge support from European community. Okay, so the outline of my talk is this. Actually, I gave a title with 3 subtitles, which are these: orbital vortex phase, orbital Edelstein effect, pi pairing, but I realize it's too much. And so I'm going to talk about, after a brief introduction, I will talk only about the first 2 topics, hopefully, or otherwise only about 1. Okay, so I think I should stay here. So first of all, I can be actually, since this is an expert audience, I can be very brief in the introductive part. But just let me say a few things, like as we all study in a textbook, we have the quenching of the orbital moment to the crystal field potential. And also we have the splitting of the orbit, but these orbitals that we have, they all have 0 projection of the orbital moment. Also we are, not all the couplings are allowed. We have some, only some coupling with same orbitals are allowed by symmetry. This kind of hopping terms are not allowed. So what happens when we break symmetry? We break inversion symmetry, we have a breaking of the MZ symmetry. This happens, of course, at surface, interface, or can be due to presence of strain, electric field. So actually, when we have this breaking of the mirror MZ symmetry, we allow this kind of different interaction. And these can be written using the orbital angular momentum operators component in this form if we are using a tight banding model, for example, on a lattice, or it can be used a continuum model. So this orbital Rashba term is the analog of the spin Rashba term, just that we replace the orbital moment we replace this polymeters with the orbital moment. And about symmetries, time reversals is conserved, C4 rotation is conserved. This other symmetry, vertical symmetry are conserved, but we have a breaking inversion and MZ. Of course, there are many works, and this is probably not complete list of references. Many of you are in the audience. And about orbital Rashba effect in conductors. I want to stress this nice review written by Dongo and collaborators that also talks about orbital effect, orbital torque, and other things. So when we have orbital Rashba effect, we have orbital textures that arise in the system. Okay, so let's go on, and let's write some Hamiltonian. So considering a square lattice, we can write the Hamiltonian for the normal system in this form, for example, and this is the orbital Rashba term. And what about superconductors? Actually, we are not considering the spin. Spin is mute in this part of the Hamiltonian. So we can simply have a number basis written in this term. So we have, this is the electron part, this is the hole part, and these are the part regarding superconductivity. So we are considering, we can also say that this is a 3-band spin-singlet S-wave superconductor. I want to stress this. We are just considering conventional superconductor with spin singlet. So about the spin, we have also, our pair is always with spin up and spin down. And about superconducting or the parameter, so this part of the Hamiltonian is diagonal. We have only pairing of electrons with the same orbital character. So, okay, let's say here I'm not sticking with X, Y, Z. I will call it ABC because we can think about the TG sector, the T2G sector of the d orbitals, or we can think about p orbitals. So let's say that the minimal description requires 3 bands, but we can be more general and just call it ABC, for example, with this. But okay, in the next of the slide, in the rest of the talk, I will use only these T2G orbitals. Okay, so what is one of the effects of the orbital Rashba coupling is that we, through the orbital Rashba effect, we have the electron wave function form a superposition. We can carry non-zero orbital angular momentum. For instance, we have this kind of term. So we can have a superposition of these two, which leads to electron density, which has then a non-zero orbital momentum, which can be +1 or -1, of course, with the h bar not written. So I'm not using the conventional color code for this, which are complex wave function, but this is actually the plot of the square, the modulus. And so I'm using this arrow, like circulating this way is up and it's +1, and circulating the other way, it's L-1. So actually also in superconductor, we have this orbital polarization. So we have, for example, this is animation that show how is varying the chiral pattern of the orbital angular momentum in a superconductor, which is, pretty much the same as in the normal system. It doesn't alter this part. Okay, so this was the introduction. Let me talk about this exotic orbital vortex phase. So the starting point we have is this zero projection wave functions, and we have, so as a starting point, orbitally unpolarized pairs. So these kind of pairs, these are the superconductor order parameter, as zero angular momentum. But since we have seen that we can form now superposition of this wave function, we have actually access to electrons which have non-zero orbital angular momentum. Actually, we can construct orbitally polarized Cooper pairs. So this is just a sketch. So we can use electrons that have this characteristic to have this kind of orbitally polarized Cooper pairs. So let me say something more about these orbital polarized pairs. So how we can construct them. Actually, it's the recipe is the same. We have this. We have to form a pair, and but we choose to have equal orbital momentum pairing. So we pair electron. We carry the same. This plus refers to the orbital angular momentum. So this is the pairs that carries -2 because there are 2 electrons orbital momentum, and this is the pairs that carries plus. And then +2 because there are 2 electrons. But what is the relation between this new this new order parameter compared to the original one? Actually, we see, so you can simply calculate, you know exactly how it's done this annihilation operator in terms of the previous one, which may call like this. This 0 refers to the zero projection of the orbital angular momentum. So we can see how is built this new order parameter. And it's made of a part which has intra-orbital channels. So this is the one that we have also in the original part. And then we have this kind of pair which couples electron with different orbitals. so these interorbital channels. We still only consider spin-singlet. And actually, okay, in our analysis, these order parameters delta, which are the original one, conventional one, let's say, are always real, so that this is the real part of eta, and this is the imaginary part of eta. But actually, with the Hamiltonian that I wrote before, we do not have this kind of terms. To have this interorbital pairing, it requires to break other spatial symmetry. So we need to break also the C4 rotation and also these other mirror MZ, MY. So this is the new Hamiltonian we are considering. Let me put some more here. And actually, we are decided to write this in real space because we want to look not only to uniform solution, but also we want to look for pair density wave-like solution, actually this more exotic vortex solution. But let's say that the ingredients are pretty much the same. And so this is this parameter. We can, okay, with this tau is the Pauli matrix for the electron and hole channels. And this T, okay, this part is the superconductive part. And so these are all these have all the other ingredients, and it's written in terms of the operator of the orbital angular momentum. So if we have a connection along, we consider a square lattice, it's the easiest one. And so if we have, we consider a bond in the x direction, we have this term, but if we consider the bond in the y direction, we have this other term. So pretty much the same. You have to consider different kind of orbital. Let's say here you have Ly, here you have Lx, and so on. So what are these terms? Okay, these are the matrices. This is simply the Rashba coupling that I wrote before. But if we write it in momentum space, it's like saying k Ly, saying ky Lx, and saying kx. This b means Ly. The next term, it's also a couple same orbitals. And so it's just an isotropic term that's compatible with the C4 point group symmetry. The new ones are this, which actually, is the anti-commutator of the orbital angular momentum operators. And these are the terms that break the vertical mirror and rotation. So how we can have this term? Well, this can be due to strain or electric field gradients. So you need to have, in order to have this interorbital pairing, you need to have very low symmetry contact in your system. And so these are the terms that have an impact on pairing. So these are the ones that activate the interorbital channel. So the superconducting part here, this matrix here, now delta is full, while before it was just diagonal. Okay, so we want to study this in a real space system. And so what are these arrows? This is just a way to display a complex number, in this case a complex order parameter, so that we plot at each side the real part and imaginary part of eta. So you can have a uniform configuration, or you can look for some more exotic kind of order parameter, which has a winding, since this is a complex number. So you can write this eta in this form, and where the real part is with the equal orbital pairing, and this is the interorbital pairing. Let me say that in both cases, uniform and vortex, anti-vortex, and you have this together, vortex, anti-vortex. You have eta plus, eta minus together. So these configurations both are with orbitally polarized pairs. But with this interorbital channel, you have more possibilities of more exotic states. Okay, just reminding of. Okay, so first thing is to study the stability of this vortex phase. I mean, we consider that we can have this kind of exotic states. Is it stable? And so we are comparing the free energy of the vortex solution compared to the uniform solution. changing the orbital Rashba parameter for a fixed value. This is a reference of the amplitude of the gap, of the superconducting gap. Of course, you need to have that delta A is different from delta C, and in the system it's like that. And so you have a threshold value for which you have a transition from uniform to vortex phase. Okay, let's skip this other, or not skip too much, this other kind of configuration where there is also a suppression of the amplitude in the vortex phase. Okay, so this it's done for one value of delta, so you can move and consider other possibilities of this reference delta 0 compared to the orbital Rashba coverage. So you have this kind of phase diagram in which you have a part in which the uniform of eta phase, I mean uniform in the sense of a uniform eta ordered parameter phase is stable, and here you get this orbital vortex phase. So that was done not self-consistently because we were fixing this delta 0, but we actually made also a study with self-consistent, looking for self-consistent solution. So this plot, what is the difference? That I teach alpha, I go and consider which is the self-consistent solution for my order parameter in the uniform and vortex configuration. And then I compare the free energy of the two solutions. And so still we have, a competition, and then you have a situation where the orbital vortex phase is more stable than the uniform phase. Of course, making this real space self-consistent analysis is quite demanding computationally. So the size was a little not small, not so big. It was 20 by 20. So, but just for few values, we consider also larger system, and we see that, you cannot see the difference here. You cannot spot the difference. We have to enlarge to see the difference. Some more detail. Okay, I still have time, but this is the first part. So some other details about this self-consistent solution. So we see that the effect of the orbital Rashba on the pairing is that you have a reduction of the amplitude in the uniform case. Okay, how can I plot the vortex case where, in the space, in the lattice, is not, you don't have all over the same amplitude. So we are just plotting the mean value and the minimum and the maximum. And so you have this kind of bands, strips that tells you how is it going, the value of the ordered parameter. So, but this is done to match with what we have done with the fixed value of this reference delta 0, because actually since we see that we have a suppression of deltas, we actually moving self-consistent analysis. We are moving more or less, this is just to get the eye, on this kind of phase. That's why we have orbital vortex phase more stable at lower alpha. This is the plot, this one. This is the reason. And also we have, when we do this self-consistent analysis, we see that the spatial dependence of the amplitude is not uniform. That's why we have this, so we have here it's a maximum, and then it's sort of reducing. Okay, so this, I skipped the animation, it's just, then we look for a hallmark of this vortex phase by looking at the orbital current. So this is the orbital current operator on a bond. So we are drawing here, it's, this arrow is what you have as a current on this bond, and this other bond, of course, this is J, A, B, and C are our orbital character. And so we see that in the vortex phase, oops, that's the uniform. I skipped this one. So we have a certain winding, which reminds the presence of this vortex phase. And this outer plane, JC, is JZ, if we want to write in terms of X, Y, Z, is not 0, while in the uniform case, we have a uniform conductor current, and this is totally 0. Okay, so let me summarize this part. To have this orbital vortex case, we state we need very low symmetry. This can be done with electric field, strains, and actually these are also the tuning parameter, because you can tune the orbital Rashba parameter and also this other Tm that is, okay, it was fixed in the analysis, which gives the extra symmetry breaking. This is also due to electric field, mainly electric field gradients, actually. So, but how can we detect all this? Well, so we see, for example, if we apply a weak magnetic field, then there will be an imbalance with the counter-propagating currents. And so there can be an anomalous flux that could be detected with SQUID. Then also this orbital supercurrent can generate electric fields, which will have this kind of patterns around the core. So also this could be a way to detect this kind of state. And at last, since the amplitude of the order parameter is not homogeneous around the core, this can be probed by STM spectroscopy. Okay, and then just an analogy. So one, he knows that in a superconductor, if you apply magnetic field, which is a source of time reverse asymmetry breaking, you can have this vortex phase, the Birkhoff vortex. So now we're saying that with electric field and low point group symmetry, so breaking spatial symmetries, you can have orbital vortex phase, which, so you don't have any magnetic field. Still, we are talking about spin-singlet Cooper pairs, so there is no net spin, but they have orbital moments. And then these are counter-propagating currents. And these currents are neutral, there is no charge. But let me say this is, the take-home message of all this is that you can have this orbitally polarized pair, also in the uniform case. This is the main point. Okay, let's move on to the second part. So the orbital Edelstein effect. If I have still time. Okay. So it has already been mentioned before, the Edelstein effect. So you have a system with broken inversion symmetry, and in this kind of system, you can, with an electric current or a presence of an electric field, you can induce a spin magnetization. This has been also studied in superconductors, also by the same Edelstein and many others. And so what is the difference here? That you have distributionless transport. But then the things are the same. You have a finite spin polarization in response to what is now a supercurrent. Then let's see what is the orbital Edelstein effect. And also, I'm lucky that I don't have to say much here in this audience. So we can have the orbital Edelstein effect. And so I put some reference here, and I apologize if I missed somebody. And let me say also that this very recent one is with an experimental observation of the orbital Rashba Edelstein. In this case, it's the magnetoresistance. So what we have done, well, we have studied the orbital Edelstein effect in superconductors. Okay, so what's the difference in superconductors is that the presence of a current bias, how do we study? Well, it gives a position-dependent phase to the superconducting order parameter. Okay, now let me say that here we have only the orbital Rashba coupling, and we don't have the other extra symmetry breaking terms that I discussed before. So the Hamiltonian can actually, this part can be gauged away in, and you can put this momentum shift, but as opposite sign for electron and all. And so now the order parameter stays without this dependence. So this is a way to study. And we have done the study with linear response theory. And we have also, okay, let me go back, just this kind of writing the system allows to make a different direct comparison between the spin case and the orbital case. because you just have to, let's say, consider this, write this for the spin Rashba or the orbital Rashba case, and then you can compare the two. And so what we find that is the signal of the orbital Edelstein effect can be much larger than the one of the spin Rashba Edelstein, the spin Edelstein effect, of more than 1 order of magnitude. And also, it's sign tunable. Okay, one can say, okay, there is a sign change also here, but you have this sign change for the spin case exactly mu equals 0, because we are considering square lattice, and so you have an extra sublattice symmetry. But here, instead, you can have the sign change, which is tunable. And let me say a bit more about that. Let's put all things together. So let's draw the normal band structure for spin and Rashba case. Okay, it's over. Oh, I haven't looked at you. Okay, so let me say that you can have a tunable system, but I want to show one thing. So, but unfortunately, I have to do like that because I cannot. Okay, this was just because I thought it's better to have it. I want to say this, that there are experiments, because, I mean, physics is based on experiment. This is what we always say to our students, so it's good to have experiments. There are experiments with electric field applied to superconductors, which are metallic superconductors. Like, for example, this is titanium, and then it has been repeated with, let's say, aluminum and, okay, in other kind of geometry, like suspended Nadon beach. But let me go back to here, because I have the list. So what happens is that you have a suppression of the supercurrent. And so one study, actually, this is how I start to study the orbital FM superconductors, because I wanted to see how this kind of model could explain such kind of experiments. And okay, so I think I now flash this, which is my conclusion. So we know that we have this important field of spintronics, and actually, very related to this is the superconducting spintronics, where you need to have the spin triplet pair. But now we are this emerging new field of orbitronics, where the driving is given by electric fields, rain, ferroelectricity, and I hope we will have the superconducting orbitronics. Sorry for taking your time. I haven't seen you when you gave me the time.